Restriction maps are made to show the relative positions of different restriction sites on a plasmid. They can be drawn either linear or circular depending on the vector in question. Since plasmids are circular, they produce circular restriction maps, but linear maps can be drawn for linear fragments of DNA. The way that we construct them is similar, but for the exam, you will need to know how to draw a circular map, and this will be the main focus of this video. So let's start by defining a restriction site, which is a sequence in the genome at which a restriction enzyme will cut. They are usually palindromic, meaning they read the same forwards as they do backwards on complementary strands. This is an example of a restriction site for a restriction enzyme EcoR1. It consists of 6 base pairs, and we can see that it is palindromic on complementary strands. Following digestion, many restriction enzymes produce short single-stranded regions at the restriction sites called sticky ends that are complementary to each other. To help you learn to construct a circular map, we will first go through a linear example. This example is a linear fragment of DNA digested with 2 restriction enzymes, HIND3 and SMAR1. The total size of the fragment is 7.5 kilobases, and so the total of the fragments produced should equal this. So we start with our line to represent our fragments of 7.5 kilobases. Then we look at the fragments produced by our restriction enzymes. We are going to begin with HIND3, which produces fragment sizes of 2.5 and 5 kilobases. If we look further down the table, we can see that a fragment of 2.5 kilobases is also present in the double digestion. We can assume that this is produced from the HIND3 restriction site, as the fragment size is present both in the single digest and in the double digest, and therefore mark it on our fragment at roughly 2.5 kilobases in, leaving 5 kilobases after that site. Next, looking at the double digestion, we can see that the remaining 5 kilobases is split into 3 and 2 kilobases by the SMARF1 restriction enzyme, which fits with the fragment sizes we get from a single digest using this enzyme. This means that the site must go after HIND3s to produce fragments of 3 and 2 kilobases. Since we have a fragment of 5.5 kilobases in the SMAR1 single digestion, this means that if we exclude the HIND3 restriction site, we need to be able to produce a fragment of 5.5 kilobases and a single fragment of 2.0. Therefore, the SMAR1 restriction site has to be 3.0 kilobases downstream of the HIND3 site, as these combined fragments would give us the 5.5 kilobase fragment produced from the single digestion. When we digest a circular plasmid with just one restriction enzyme, this will only produce one fragment that has the same molecular weight as the original circular plasmid. We can see this in the above example of BAMH1 cut to a circular plasmid. When digested with BAMH1, we produce a linear fragment of the same molecular weight that either begins or ends with the BAMH1 restriction site. Therefore, when we digest with 2 restriction enzymes, each with a single site, we produce 2 fragments. So to approach drawing the circular restriction maps, we first digest the plasmids with the restrictions as single digests. This will tell us how many restriction sites each enzyme has on the plasmid. In a single digest of PBr607, we get only one fragment produced with a molecular weight of 2.6 kilobases. This tells us that each restriction enzyme has only one restriction site in this plasmid, as the cut turns the circular plasmid into a linear segment of DNA. To make a restriction map, we begin with a circle and put the restriction site for one enzyme at 12 o'clock. Whichever enzyme appears at the top of the map is arbitrary, so here we will use BAMH1. We will next look at the double digestion with EcoR1. We get fragments of 2.4 and 0.2, so we will make the first restriction site as EcoR1 0.2 kilobases away from BAMH1. Now we need to identify the position of PST1 on the plasmid. We know that this enzyme only makes one cut, and looking at the triple digest, we can see that we need to produce fragments of 0.46 and 1.94 by making this cut, as we already have a fragment of 0.2 made by BAMH1 and EcoR1. We do this by using the PST1 site to bisect the remaining 2.5 kilobases to give us 1.94 and 0.46. This gives us 2 possibilities of where we could place the PST1 site, either closer to the EcoR1 site to give fragments in the order of 0.2, 0.46 and 1.94, or we could place it closer to the BAMH1 site to give an order of 0.2, 1.94 and 0.46. But to identify where it actually cuts, we can look at the double digest of EchoR1 and PST1, where we see fragment sizes of 0.46 and 2.14. This tells us that the PST1 site should be close to the EchoR1 to give a fragment order of 0.2, 0.46, then 1.94 kilobases. If we have a restriction enzyme with multiple restriction sites in one plasmid, we can usually tell from the single digest, as in circular plasmids this will produce more than one fragment. Here we have a hypothetical example of a circular plasmid digested with EchoR5, and this produces 2 fragments. We know that this must mean that there are 2 restriction sites, as having one site produces one linear fragment from a circular plasmid of the same length, and a second restriction site will bisect the linear plasmid to generate 2 fragments. So how do we apply this to construct maps with restriction enzymes featuring more than one restriction site on the plasmid? Here we have an example of a plasmid with a total molecular weight of 20 kilobases. When we digest it singly with just EchoR1, we get fragments of 9 and 11 kilobases. This tells us that the plasmid has 2 restriction sites for this enzyme, as 2 sites produces 2 fragments in a circular plasmid. When we digest the plasmid singly with BAMH1, we also get 2 fragments produced, suggesting 2 sites. To find out the order of these restriction sites, we'll begin with BAMH1 and put one of the sites at 12 o'clock. The second BAMH1 site is 5 kilobases from the first site, as seen in the single digestion, and this can be placed at 3 o'clock on the map. We can then compare the BAMH1 single digest to BAMH1 EchoR1 double digest. The double digest does not contain either the 5 or 15 kilobase fragments seen in the single BAMH1 digest, showing that each of the 2 BAMH1 fragments has a single site for EchoR1. The EchoR1 site in the 5 kilobase fragment generates fragments of 2 and 3 kilobases, so we can place the first EchoR1 site 3 kilobases to the right of the BAMH1 site at 12 o'clock. Now we can ask where the second EchoR1 site lies in the 15 kilobase BAMH1 fragment. We know that the single EchoR1 digest gives fragments of 9 and 11, so the second EchoR1 site could lie either 9 or 11 kilobases clockwise from the first EchoR1. Only the first possibility is consistent with the fragment sizes found in the BAMH1 EchoR1 double digest. If the second EchoR1 is 9 kilobases clockwise from the first EchoR1, the distance between the second BAMH1 and the second EchoR1 site is 7 kilobases, and a fragment of this size is found in the double digest. If the second EchoR1 was 11 kilobases from the second BAMH1 site, then the distance between the second BAMH1 and the second EchoR1 would be 9 kilobases, but a fragment of this size is not found in the double digest. With the second EchoR1 site at the correct position, all the fragments expected from the double digest can be generated.